Hey guys, I will be doing this presentation on using machine learning techniques to label data sets that will be used in other supervised learning algorithms. And I will be using Tesla as an example for using this technique. So to begin, let's think about some of the data sets that we've already seen in this class to start off with. Of course, we have the pinnacle of this class. We have the Is It a Good Day to Fish data set. We also have the iris data set, the digits data set, the contact lenses data set, and because these were used in supervised learning, they all have labels. All of these data sets have to be labeled with the correct specification of what you expect your algorithm to output. And in the case of these data sets, that was probably done manually by humans. And that's fine with these simple data sets. Most of them are yes or no. It is a good day to fish, it isn't. Or at the most complex, this is a number 2 or this is a number 5. That's relatively easy to label. But what if we are dealing with more complicated data sets? What if you need to add labels to videos or images? Now all of a sudden, these human annotators are likely to screw up at times and misinform our algorithm. They are likely to take a while, and you need to pay your workers. And even if all of this is fine, even if your workers could be free, they will take time, and it would be much quicker if we could automate this process. Which brings us to Tesla. If you don't know, Tesla is one of the leaders in self-driving technology, and they use cameras that are scattered around the car to give their convolutional neural network the data that it needs to make predictions on the road. Now Tesla found out the hard way that human annotators can be costly and slow in the first 2 algorithms that they implemented within their neural network. The first was lane detection, where they had to use human annotators to basically draw out these lane lines, and it had all the issues that I mentioned before. They also used human annotators to implement object detection. Here you can see that the Tesla is able to differentiate between pedestrians in yellow boxes, vehicles in red boxes, motorcyclists in blue boxes, and bicyclists in green. Now, using these two algorithms that were humanly annotated, each Tesla is able to create a digital environment around itself based off of what it is detecting through its cameras. So this image is actually taken straight from the UI out of a Tesla, and you can see that this UI is showing the lane lines that it's detecting and all of the cars that it's detecting on the road. And with this digital environment, Tesla was able to create something that they call fleet learning. And this is the diagram that they use to explain that in their Automation Day presentation. I'll give you a brief overview. This presentation that I am giving focuses on the labeling arrow of this. So it starts with the car itself. The car, the video that is recorded from the cars is what is used in all of the data sets. Now, these cars are able to be constantly making predictions while they're driving. And if they ever make a false prediction, that inaccuracy will be sent to Tesla. And then Tesla can add other instances of this inaccuracy into the data set, which is already automatically labeled by the cars themselves. The neural network will then retrain and then redeploy to Teslas on their network, and then this cycle will repeat up until whatever they're trying to implement, the accuracy of whatever algorithm they're trying to implement is at a point that they deem acceptable. Now, one example of fleet learning in action was Tesla implementing their cut-in detection. Now, cut-in is basically whenever a car merges from their lane in front of a Tesla at a distance that is relatively dangerous. Now, because Teslas already have their digital environment, they already are able to detect when a car moves from one lane to another. So you can take the video recorded at that moment and add that into a cut-in data set, essentially. After a while, after the millions of Teslas on the road detect enough cut-ins, you can have a very large data set that you can then use to train a neural network that would be very accurate at detecting cut-ins. And this would all be short clips of cut-ins that actually happened in practice. And because this was all developed from the digital environments within the Tesla software, no annotators actually needed to go through and highlight the moment that the car crossed over the lane divider. No annotator needed to highlight where the car was at the time that it cut in. None of this needed to be done. And this was all automatic, which, because this is how Tesla has implemented their neural networks, it puts them in a great advantage where essentially they just need to code up whatever they want to be detected. And then eventually their Teslas should be very good at predicting when that event will occur. Thank you guys very much. I think I went a little bit over. If you want to know more in much more eloquent speech, I would highly recommend watching the Tesla Automation Day presentation. It's 3 hours long, and it goes extremely in depth with how they have implemented their neural networks, their software, their hardware, everything. Thanks a lot, guys.